chapter 7 is called the normal probability distribution. The first two things are just saying, in chapter 6 we learned about discrete probability. Discrete meant countable. So it's just like how many free throws did you make, or how many classes are you taking, that kind of thing, where we would just have those charts. And then we'd have the corresponding probabilities with the charts. 6.2 we learned about the binomial, which was just a specific type of discrete where we had two outcomes. But we don't all have discrete variables. There's all those continuous variables. Remember, continuous variables mean you have to measure them. So like time, volume, all those variables that have some kind of continuous variables has its own distribution, and most of them are the normal distribution, okay? So that's why chapter 7 is so important. Before we get to the normal, we need to talk about the uniform first. So let's look at objective 1. It says, use the uniform probability distribution. We will illustrate a uniform distribution using an example. Using the uniform distribution makes it easy to see the relationship between area and probability. And that's the key thing, guys. From now on, area is going to be probability, okay? So whatever we shade, that amount that we shade, is going to be consistent with the probability of that random variable occurring, all right? So let's look at the example they have us doing. It says, suppose you have a friend who's always late. Do you guys have that friend?
Yes.
And if you don't, you are that friend?
Nope.
I'm just joking. So it's one of those things where you know your friend's going to be late, so you tell them to meet you like 30 minutes before you really even want them to be there, and they're still late. So say you have a friend who's always late up to an hour, meaning after an hour they call you and say, I'm not coming, all right? So let the random variable x represent the time in minutes from when you were supposed to meet. So aka, x is how late that friend is, or how many minutes. So what are our boundaries? What if your friend actually shows up on time? What would x be? If x is representing the number of minutes that it's late, but they show up on time, how many minutes late are they? 0. So that's the lowest, right? And then say they're completely 1 hour late, which would be 60 minutes, all right? So they're kind of giving us this bound. This random variable can be anywhere between 0 and 60. Like literally think of a clock, right? You could land anywhere on that clock within a minute and say I'm 23 minutes late or 42 minutes late, whatever it may be, okay? So suppose the 1 minute time intervals between 0 and 60 are all equally likely to occur. That is, your friend has the same probability of showing up 6 to 7 minutes late compared to 42 to 43 minutes late. Because any two intervals of equal length between 0 and 60 are equally likely, the random variable is called a uniform probability. And we'll put distribution in there. Because what's it mean to be uniform? All the same, right? Way back when in chapter 3, we talked about different shapes of the graph, and that's where we were introduced to left skewed, right skewed, bell-shaped. One of them was uniform when all the bars were remotely about the same height. This is the same kind of idea. Every minute has the same chance of being likely, and so everybody has the same probability. All right, so we have something in here where I almost need to like bold-face it. Let's star it. This note is pretty important, okay? Why? Because any specific number from here on out has 0 as the probability, because it is a continuous random variable. You cannot be exactly 6 minutes late. You're 6.1 to 6.2 minutes late. You have to have an interval, okay? So that's kind of a trick question from here on out. If they say, what's the probability that your friend's exactly 6 minutes late, you would just say 0. I have a 0% chance of that happening. You need a time interval. The second one is kind of told up here. Any interval of equal length has the same probability, all right? So let's see if what I just said made sense. Let's use it to fill in the blanks here. What would be the probability of your friend arriving exactly 33 minutes late? Keyword exactly 33 minutes late. Say it louder. 0. It's a continuous random variable. 33 does not exist, okay? Is that 33.001? 32.999, right? So it can't occur exactly, so that will be 0. The second thing says two intervals of equal length have the same probability. So let's look at the second thing. The probability of your friend showing up 10 to 15 minutes late is exactly the same as him showing up 50 to what?
55.
How'd you know?
Because 10 to 15 you add 5.
it's that 5-minute interval, right? So if we want the same probability, this is a 5-minute window. This needs to be a 5-minute window if we want it the same, okay? If we want it longer, we'd make it a longer window. If we want it shorter, we'd make it a shorter window. But if we want it exactly the same, it has to be the same length. All right, blah, 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 blah. All right, so what we have is if all these things are met, if everything's a continuous random variable and that they have the same likelihood of occurring, we can start talking about how it is a probability density function. And all that is an equation, okay? And this equation can be graphed and used to compute probabilities. But guess what? It has two properties that it must satisfy. But these two properties, guys, mimic the two properties we just reinforced, when did we do it? On Wednesday of last week, that what do we know about every single individual probability? It has to be between what two values? Every probability has to be between what two values? 0 and 1, right? It can't be negative, it can't be more than 1. And then what do we know about the sum of the probabilities? They all have to add up to 1. These two notes are the exact same thing. It's just for continuous random variables now, okay? So it just says the total area under the graph of the equation over all possible values of the random variable must be what? If it's a total area and area represents probability, what must this be equal to? 1, okay? So that's what's going to be the newest thing to kind of comprehend, is that now instead of like these little charts that say the probability is this, this, and this, it's going to be a graph because it's this continuous curve, all right? And when we graph it, whatever we shade, that area represents probability. So if we have the total graph, that represents all the probabilities, and we know all the probabilities must be equal to 1. All right, number 2 is kind of that between 0 and 1 concept. The height of the graphic equation must be greater than or equal to 0, okay? So you can't have a negative. For all values of x, that is, the graph of the equation must lie on or above the horizontal axis. So again, probabilities can't dip below 0. All right, so what the heck does this look like? Let's draw a probability density function for our example above, okay? So we're going to draw an x and y axis. We're going to draw an x and y axis. This is going to be our random variable time. It's the random variable time in minutes. And this is new, but this is the actual density function. How many of you guys took college algebra or like kind of algebra 2 or something in high school, right? A function's just a fancy word for line, right? A function, you have to pass the one-to-one test, all that kind of thing. So what we're going to do is these different continuous probabilities have their own graphs, all right? But what would the graph of a uniform distribution look like? Well, what kind of line would we have if they all have to be the same height? It's just a straight line, guys, okay? So our density function is not very exciting. It's just this rectangle. Not very fun at all, okay? But we can kind of start labeling this rectangle, all right? Because this x-axis represents our random variable. And if we go all the way to the top, we're talking about our friend that's late. And remember x was the amount of time that he could be late. So what was our lower bound? If he was on time, what is this? How many minutes late is he? 0. And then what was our upper bound? We're only giving him an hour, so what was that? 60, okay? So the question is, what is the height right here? Like, how do we label this? Well, there's a little bit of math that has to go on. What do we know about this total area? What does it must equal? Yep. So, believe it or not, we have enough information to figure out the height of the graph. Why? What shape did we just draw? A rectangle, right? How do you guys find the area of a rectangle? Length times width, right? So we know the area of the rectangle equals 1, and we know its length is 60, so can't we figure out its width? We sure can. So if you need to, just off to the side, let's write that. Area equals length times width, but we know the area equals 1, and we know the length is 60. So we should be able to figure out W. What do I need to do to isolate W? Divide by 60. So W equals 1/60. So I'm going to label that. That's this height right here. And you're like, okay, so what? What does any of this mean? Well, think about a clock. How many minutes are in an hour? 60, right? And if every minute has the same likelihood of occurring, what's the probability that any 1 minute would occur? 1 out of 60. So that's all kind of comes full circle, okay? Because remember, this is supposed to be kind of our probability. Every single little minute interval has a 1/60th chance of occurring. It's uniform, so it's all one even length. And you're like, okay, well, what's the point of this? Because now that we have this drawn, we can shade any little time interval in there, find the area, and we've actually found the probability. So let's go ahead and flip the page to the top of page 2. I got this straight out of your book, so I'm trying to mimic your questions as much as possible, okay? So it says, how the heck do we use this graph to find the probabilities? Well, all we're going to do is multiply the width, the length of the time interval, times the height of the rectangle, in this case, 1/60th, okay? So our width will be our width, and our height will be 1/60th. So, with that being said, what's the probability that your friend will be between 21 and 25 minutes late? Well, if we could look at our graph, what kind of time span is that? How many minutes? Say it louder.
4.
That's a 4-minute time span, right? So if you wanted to, you don't have to. Maybe I'll do it to mine. You guys don't worry about doing it to yours. What we could do is we could say, okay, 21 to 24 minutes would be something like this. Right? And what did I just draw? A really skinny bar, aka a rectangle, right? Why did I put 24? It's 25, isn't it? Okay. So, how do you find the area of a rectangle? Length, which is what? Times width, which is 4. And we'll get the probability, okay? So let's do that real quick. So we're just going to take length. So the probability is the area, which is length times width, right? So what was our length? 1/60th. What was our width? 4 minutes. Is everybody okay? That's a 4-minute gap. Oopsie, I'm writing on stuff you can't see. Does that look okay? What do you guys get when you put that in your calculator? 1/15th. Or what we can do is we can put it as a decimal, because to me that makes kind of more sense, like to see that decimal. So I think is that 0.6 repeating? Okay.
Yeah.
Or as a percent, that's 6.6% repeating. What the heck does that mean? Well, it just means if every minute has the same likelihood of occurring and we're worried about a 4-minute interval, there's a 4 out of 60 chance of that occurring, which reduces to 1/15th. So about a 7% chance that he would show up in that time frame, okay? So anytime it asks for probability, it's asking for the area, okay? Anytime it asks for probability, it's asking for that area. So just figure out the width and then multiply it by the height, all right? But then they go backwards. They say, okay, it's 10 o'clock, and there's a 20% probability that your friend will arrive in the next blank minutes, okay? What have they given us? They have given us the probability, which means they actually have given us the area, right? So again, we have probability equals area, which is length times width, but what did they give us? They gave us this time. Don't we still know the length of the rectangle? How tall is it? What don't we know? The width, okay? So what they have done is they have shaded a chunk. They have shaded 20% of our graph, okay? They have shaded 20% of our graph, but if we know the graph has a height of 1/60th, we can figure out how wide that rectangle is. So how do I isolate W? Divide by 1/60th, aka multiply by 60, right? So what do you get when you take 0.20 and multiply by 60? 12 minutes. Do you guys agree that 12 minutes is a fifth of an hour? How good are we with our 12s, right? 12 times 5 is 60. Sometimes our 12 times table is not the best. So hopefully that makes sense. We shaded 20% or a fifth of our graph, right? So 12 minutes is a fifth of an hour. So he's going to show up in the next 12 minutes, aka he's going to show up at 10:12. At 10:12. Okay, so this is how your My Math Lab is going to start. They're going to start with this generic random uniform distribution where every uniform distribution is just a rectangle. Okay, so we're using it to find area because the area is the probability. So if you have length and width, you can multiply that to get your probability, or vice versa. They might get you the area, aka they give you the probability, and you can find your width. Okay. So that's how I think your first two problems are on 7.1. But in real life, barely anything is uniform. Like the likelihood of your friend being late, my friend's really, really late. So like I don't think every minute has the same probability. Like it probably, what would that be, less skewed. Like they have more likely to be like 30, 40 minutes late versus 10, 15 minutes late. So real life is not uniform, all right? So what we're going to get into is the normal curve, but what they want you to take away from this is area is probability. Area is probability. From here on out, if they ask area or probability, they're interchangeable, all right? So let's start talking about the normal curve. A continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram has the shape of a normal curve, aka a bell curve, okay? This is a lot more realistic in real life, okay? A lot of things like, for example, like height. In general, most people are around this average height. Some are shorter, some are taller. Weight, same idea. Most people are around this average weight. Some are heavier, some are lighter. So a lot of things follow this bell-shaped curve where a majority of people are in the middle, and then we kind of have those little bounds. So this is more important than a normal distribution. So this, again, it's kind of a section that's not very exciting. I probably could have given you the notes in the book and said just fill it in, but hopefully I can make a little bit more sense in the book. We're going to draw the normal curve, and every time you draw the normal curve, the mean and the standard deviation have specific roles, okay? So the mean, guys, is always in the center. So worst case scenario, if this problem's like blah, 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 normal curve, the least you could do is draw a normal curve with the mean in the middle, all right? The values mu minus sigma and mu plus sigma are called inflection points. So those that took calculus, that should sound familiar. Inflection points are where your curve changes from upward to downward, okay? And what do I mean by this? This is concave down, where it's curved like this, but at its inflection point, it changes to concave up. That's exactly one standard deviation away from the mean. Why is that important? Does anybody remember the empirical rule? 1 standard deviation out, 2 standard deviation out, 3 standard deviations out. So 68% of our data, right, lies within this, 68% of data lies within those two, right? So keep that kind of in mind. All right. Next thing we want to keep in mind is that your normal curve, guys, we can make one for every combination of mu and sigma. So no matter what we're talking about, test scores, weight, height, speed, anything that's a continuous random variable, we can make a normal curve with a mean in the middle and the standard deviation out to the left or right. They'll look different shape-wise. Some will be squatty, some will be tall, but they'll have some things in common too. So let's talk about this. The first one is mu shifts the curve. Mu shifts the curve. So your mean shifts curve. Mu shifts the curve, and hopefully that makes sense. If you think about a number line, if we're talking about test averages, and the test averages is a 75, that curve's going to be way over here, versus if we're talking about, I don't know, anything that might be small, like shoe size or something, that's going to be over on where, 9, 10, 11, 12 are. So where our mean is, it's going to shift the curve. But the shape looks the same as long as your standard deviation is the same. So first couple assignments on your homework, it's going to ask which one has a mean of 0, which one has a mean of 3. You'll pick this curve has a mean of 0, because they won't have it labeled, but 0 comes before 3, okay? So all your location is based on that. Go ahead and flip it to the top of page 3. So different values of sigma shift the curve up and down. So standard deviation changes shape. Standard deviation changes the shape. Are you a big, fat, squatty curve? Or are you a tall, skinny curve? And hopefully we can make sense of that. I'll probably ask you many, many times, I'm not joking, it's going to be on your last test, but what does standard deviation mean in words? The distance away from your mean, right? So if we have a small standard deviation, that means everybody's really close to the mean. So we got to shove in close, really close to the mean, but we know the area has to be 1. So what happens when you squeeze things? Where's the only place they can go? Up, okay? So notice this tall, skinny one has a smaller standard deviation versus this fatter, squattier one, because it doesn't have to be as compact, okay? It's the spread of the data. This has a small standard deviation, so it's not as spread out as the wider, okay? Again, keep that in mind. They'll give you 2 graphs like that, not telling you the standard deviations, and they'll just say which one has 1, which one has 2. Smaller standard deviation means you're more compact. All right, this is the part I'm talking about. You don't need me for this at all, but let's just go ahead and fill it in. Your curve is always symmetric about the mean. So the mean's always in the middle. Your curve is always symmetric about the mean. So like I said, no matter what, draw that curve and then label the mean in the middle. All right, since it is a bell-shaped curve, not only is the mean in the middle, but so is the median and the mode. And they all occur at that highest point, okay? Kind of keep that in mind. All right, the inflection points isn't that big of a deal, but that was mu minus sigma and mu plus sigma. And after we fill these all in, guys, I'll go back and star the ones that are really, really important to kind of keep in mind. Number 4 is something we talked about already. Since this is representing probability, the total area under the curve, so the total area is always 1. Number 5 is just something to keep in mind when we get into calculating. If you remember this trick, it will help you. If you don't remember it, you're not screwed, okay? But it just says, if we know the total area under the curve is 1, but we know the mean's in the middle, we know the curve to the left is the same as the area of the curve to the right, which means that they each have an area of what? Like if we split the curve in half, what's the area on each side? 50%. You guys get that? We know the whole curve is 1, and it's symmetric. So if we split it right down the middle, the area to the left of the mean is 50%, the area to the right of the mean. And again, keep that in mind because that's like a little trick you can kind of remember down the road. Like, oh, I don't even need to calculate it. I know that's 50%. All right. 6, as x increases, the curve goes to 0. As x decreases, the curve goes to 0. Have you guys heard of the word asymptote? So y-axis is asymptote. That's something that I think is kind of cool. I'm a weird math person, though. This gets asymptotically close to the y-axis, but it never crosses it. So basically, it goes on and on forever, but the area is exactly 1. So it's a shape that goes on forever, but the area is exactly 1, which is kind of neat how that all works. That's what I got to prove in my stats class. It wasn't fun. I'd rather be doing this stuff. All right. Last thing is to remember, guys, that if we have a bell-shaped curve, we kind of have an approximate, they call it a rule of thumb, right? So what we have here, if we're 1 standard deviation out, what is that? 68%. If we're 2 standard deviations out, how much of the data do we have? 95%. And if we're 3 standard deviations out, what do we have? 99.7%. So, up until now, this was the only way we could calculate probability. Remember, we would just add up these chunks and go from there. This was all an approximate. Notice it says approximately, approximately, approximately. We now are going to have a way to actually calculate that specifically, all right? So that's actually what Objective 4 is kind of getting us into. So what is the role of this thing? Like, why do we care about this? Is because if we have a continuous curve that follows the normal distribution, we're going to start shading chunks, and we're going to be able to calculate those chunks, and that will be our probability. So let's go ahead and look at the top of page 4. If you look at the top of page 4, it just shows you what we did way back in chapter 2. So in chapter 2, when we had continuous variables such as height, we could make a frequency histogram and group them. But what shape in general does it have? A bell-shaped curve. And so what we can do is we can use this bell-shaped curve, and what's the formula? Look at that. If that doesn't make you throw up, I don't know what will. That is the formula for a normal probability density function. Look at that. How many different values can we throw in there? It's like, oh, we haven't used sigma yet, let's throw that in. We haven't used pi yet, let's throw that in. So let's talk about it, but I just want to give you kind of a heads up. You never need to calculate it, okay? So as scary as it is, you don't ever have to do anything with it, okay? How is a normal probability density function calculated? Meaning, how do they get all these heights of y? How do they get all those heights? Well, the first thing is, notice e is here. Do you guys remember what e is? Did anybody ever learn the exponential function in college algebra? Exponential function? It's 2.71, okay? They take e and raise it to the negative of each value minus the mean squared all over 2 times the variance. That's just the exponent of e. And then the coefficient of e is 1 over sigma times the square root of 2 pi. So for every value of x, so every amount of minute that friend is late or every height, they would plug it in, do this math, and that's how they would get the height of this function. What's great is, as complicated as it is, we'll never calculate it. We're going to use a chart where somebody has done it for us. The key thing, though, guys, is that the areas are the probability. So let's use that to make sense of it. So I'm going to use this example right here. Anybody like giraffes? Sometimes people know. Okay. Go to the zoo. Say we go to the zoo, and we are looking at a giraffe. Assume the distribution of how much a giraffe weighs has an average of 2,200 pounds and a standard deviation of 200 pounds. And we're just out there looking at the giraffes, and we want to know, hey, what does this area to the left of 2,100 mean in terms of weight of a giraffe, all right? So notice they drew the curve. And where is it centered? At 2,200 pounds. That's where it should be. That's the mean. Inflection points are about 200 and 2,400. But what would the interpretation of the area to the left of 2,100 be? Guys, do this with me. At 2,100, draw a line straight up and shade the area to the left. This is where, if you're bored but you're artsy, you can have a lot of fun, okay? Have fun shading these areas. I don't do anything fun. I just put lines so you know that it's shaded. Okay? What does this mean? What the heck does this mean? And again, it's a really hard concept. Like I have to remember as a student, I really struggled with myself. The whole area under the curve is the probability of how much